So today's lesson is going to be looking at simplifying numeric expressions. We're going to start by reviewing basics that you should know from intermediate school, and then we're going to build off that and see how it applies to more algebraic level problems. So first, let's just talk about what's a numeric expression. So numeric expression is made up of add, subtract, multiply, or divide operations, as well as constants. And constants are just values that don't change. So we have no variables here. It would be the number 10, the number 3, -7. Those are all constants, examples of it. And so when you were little, you probably heard PEMDAS. Please excuse my dear Aunt Sally, as a way to help you remember order of operations. And we're just going to slightly change that now that we've gotten older. So when you were younger, the only type of grouping symbol that you knew about really was parentheses. So that's why we did that, PEMDAS. But now we're changing it to a G because we will do all grouping symbols first. So that includes parentheses, but it's also going to include square root symbols. It will also include fraction bars. So we will simplify inside of the grouping symbol before we move outside of it. After that, then we go to our exponents. We'll do our powers. Then we move to multiply and divide, and they are of the same level. So the trick is you're just moving left to right. Whatever you see first as you move left to right, that is what you'll do first. So if you see multiplication first, you do multiplication first. But if you see division first, you would do division first. And then same thing for add and subtract. It will always be done last, but it's whatever you see first is what you do first. So our first three examples are examples that you should be very familiar with. So we're just going to walk ourselves through and make sure that we remember how to do these. So first thing I'm going to do is I'm going to go inside that grouping symbol, and I am going to go ahead and simplify that. So right now I've got 48 over 2 cubed times 3 plus 5 times 4 minus, and 5 minus 3 is 2. Okay, so now I'm going to stay inside of that grouping symbol. And remember, this fraction bar is also considered a grouping symbol, so we can simplify top and bottom. So the top numerator is already simplified. 2 to the third power, 2 times 2 is 4, times 2 is 8. And then we've got times 3 plus 5. And now we can simplify 4 minus 2 is 2. Okay. Then next, we're going to go ahead and I see division, so I'm going to divide. 48 divided by 8 is 6. And then I've got times 3 plus, and now I see multiplication, so I can go ahead and multiply. 5 times 2 is 10. I still see multiplication, so next I'm going to go 6 times 3 is 18. And then I will finally do that last addition. 18 plus 10 is 28. And so this numeric expression simplifies down to that constant 28. All right, we are going to now look at the next problem. And again, we're going to start off by simplifying the numerator and the denominator. So that fraction bar acts as a grouping symbol. So first, we've got to simplify the numerator. So I am going to go ahead and do my exponent. 2 times 2 times 2 times 2 times 2. So 2 to the 5th is 32. And then I'm going to go ahead and multiply. 6 times 2 is 12. And so I can say 32 minus 12 is going to give me 20. All right, now I need to simplify the denominator. So for the denominator, I see multiplication. So I've got 27 minus 15 minus 2. And so now I just have a big subtraction problem. 27 minus 15 is 12. 12 minus 2 is 10. And then last but not least on this, I'm going to go ahead and divide. 20 divided by 10 is 2. So this expression simplifies down to the constant 2. All right, next one, I've got a big grouping symbol of a square root. Now, I'm not going to worry about the square root until what's underneath the square root symbol has been simplified. So the first thing I'm going to do is I'm going to come here to this parentheses. So I know I've got 3 plus 4 minus 2 is 2 cubed divided by 4 times 3. Okay, I still have this square root symbol that's acting as a grouping symbol, and I'm not doing anything with it yet. Next, I'm going to go ahead and do my exponent. So I've got 3 plus 2 times 2 is 4 times 2 is 8. And then I've got divided by 4 times 3. Again, I still have that grouping symbol. I'm not doing anything with it yet. And now I'm going to go ahead and I am going to do division because I see it first. So 3 plus 8 divided by 4 is 2, and 2 times 3. I'm still working on simplifying inside the square root symbol. So now I'm going to go ahead and I am going to say, okay, let's multiply. So 3 plus 2 times 3 is 6. Now I'm ready to do addition. 3 plus 6 is 9. And now I can finally come back and worry about the square root symbol. And the square root of 9 is 3. And so right there, that is what it simplified to. So these are all problems that you should be fairly familiar with. So now we're going to go inside, and now we're going to be looking at examples where we are trying to simplify radicals that do not turn out to be rational. So example 3 was an example of a radical, a square root symbol, but it simplified down to a perfect square. So my answer was rational. So now we're going to look at what happens if I do a problem and it simplifies down to a number that is not rational. That would be called irrational. These, again, should be familiar words. And so we are really going to live in the land of perfect squares. And so when we take a radical expression and we look at the number underneath the radical symbol, which is called the radicand. So I look and I see this 12. And the second I say, okay, 12 is not a perfect square, I need to think about what is the biggest perfect square that's hiding inside of 12. So what out of this list of perfect squares, what's the biggest one that goes into 12? And hopefully you're going, oh, well, Mrs. Stroll, that would be 4. Good job. And then 4 times what gives me 12? And you would say 3. Okay, and how we're getting that is it's really just saying we're taking the square root of 4 times the square root of 3. And that's this property right here. And now that I've done that, I can get this into what is called simplest radical form. So the square root of 4 is 2, and then the square root of 3, there's nothing else I can do with it. So radical 12 is the same as 2 radical 3. It's still an irrational number. I can't do anything about that. But now I've written it in what's called simplest radical form, which is something we will use a lot in algebra class. Okay, we are going to do the exact same approach for 500. So 500 is not a perfect square. I go through my list of perfect squares, trying to come up with perfect squares that'll go into it. For example, I know 25 will go into it, but I'm not going to pick 25, even though it's a perfect square, because my goal is to find the biggest perfect square that'll go into it. And hopefully you're going, ooh, that would be 100. And you are correct. And 100 times what? Well, that would be 100 times 5 gives me 500. So this is really just saying what's the square root of 100 times the square root of 5. And now it's time to go ahead and simplify. The square root of 100 is 10, and then we're left with radical 5. Okay, now what happens if underneath the square root symbol there is fractions? So the first thing we're going to look for is if the denominator is a perfect square, we are golden. The one and only rule when we are simplifying is that we can never, ever, 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 ever have a non-perfect square in the denominator. It can be in the numerator, but it cannot be in the denominator. So I automatically know that the square root of 9 is 3. Okay, I'm good with that. But now I need to come up here, and I've got radical 24. And I know that radical 24 is the same as 4 times 6. And again, I'm just taking the square roots of each of those. And so the square root of 4 would be 2, and then I've got radical 6. Okay, and now to decide if I'm done or not. You are going to hear Mrs. Stroll do this chant, inside with inside, outside with outside, inside with inside, outside with outside. And what this means is I look at the numbers on the outside of the square root symbol. And if they have anything in common, I can simplify. I look at the numbers on the inside of the square root symbol. If they have anything in common, I can simplify. But I cannot simplify something on the outside with something on the inside. That is not allowed. So 2 and 3 have nothing in common. So I now know that this is the simplest radical form of my original problem. Okay, example 7. I look and the denominator is not 5, is not a perfect square. So before I panic, I go ahead and say, ooh, could I simplify this whole problem? So 40 divided by 5, that can be simplified. 40 divided by 5 is 8. And now I'm good to go. I don't have to stress out. I have what I need, and I'm back up to no more fractions. So now I'm going to say, okay, well, 8 is really just 4 times 2. And then I'm going to square root both. And so that's going to give me 2 radical 2. And that is now the simplest radical form of that problem. Okay, last problem. 8 is not a perfect square. Oh, but 8 and 5 can't simplify. So now I'm stuck with this whole idea of I have to rationalize the denominator. And rationalizing the denominator sounds complicated, but it's really this simple. We are going to rewrite this fraction into an equivalent form so that the denominator is a perfect square. One easy way to do it is just whatever the denominator is, multiply both top and bottom by that number. So I could take 8 times 8, 5 times 8. I now have 64 on the bottom. I have a perfect square. The problem is I just created really big numbers. And I always try to create the smallest fraction that'll work if possible. So instead of multiplying top and bottom by 8, which is a great option, I go, you know what? If I just multiplied the top and bottom by 2, I now have a perfect square in the denominator. And that perfect square is 16. And 5 times 2 is 10. And if you look, it is a different fraction, but 5/8 and 10/16 are equivalent. So everything I've done is legal. And so now to simplify it, I just square root the top, and then I square root the bottom. And my goal has been accomplished. The bottom is a perfect square, so the square root of 16 is 4. And then square root of 10. There's no hidden perfect squares. It's not a perfect square, so it's already simplified, square root of 10. And again, my chant's going to come into play. Inside with inside, outside with outside. And 10 is on the inside, 4 is on the outside. So even though they're both even numbers, I can't simplify them because they are not both inside or both outside. So that is my simplified version. All right, last but not least, what if I have an expression with multiple radicals in it? How could I go ahead and simplify those? So let's look at some radical expressions. So again, my chant, inside with inside, outside with outside, is still coming into play. So if we have a multiplication problem, it's as simple as this. I take the 2 outside numbers and I multiply them. So 2 times 4 is 8. And then I take the 2 inside numbers and I multiply them. And 3 times 6 is 18. Now, I would be all done if 18 had no hidden perfect squares inside of it. But I already am thinking to myself, well, I know one way to break apart 18 is 9 times 2. So there is a hidden perfect square. So this is really 3 radical 2 times, and I still have that 8 that's out in front. So the final simplified radical expression would be 8 times 3, because those are both outside numbers. So that's 24. And then radical 2. So I've got 24 radical 2. All right, let's look at this example. So on this example, I am going to first, in order to combine these, I have to be adding like terms. Just like with fractions, you have to have like denominators. Just like with variables, you have to have like terms, same variable, same power. Same thing here, we have to have what's called like radicals. So before I can add or subtract anything, I have to try to make these radicals match if possible. So first thing I'm going to do is I'm going to say, okay, well, I know 18 is going to break into 9 times 2. So this is 3 radical 2. And then I'm going to go 2 times 3. So this one turns into 6 radical 2. All right, that one has been simplified. And then I'm going to put my plus sign. All right, and I know 8 can simplify into 4 times 2. So square root, that would be 2 radical 2. I've got my 2 and my 5. 2 times 5 is 10 radical 2. All right, and then I have my minus. And I can break 32 into 16 times 2. So that would be 4 radical 2. And then I can take 7 times 4, which is 28. All right, now that all of my radicals are the same, I've created what's called like radicals. And that part's done. I'm just going to say radical 2. And now I'm going to take all these outside numbers, and I'm going to go ahead and just add them. So 6 plus 10 is 16. And then 16 minus 28 would give me my negative 12 radical 2. And we have simplified it. All right, that is the end of today's lesson on simplifying numeric expressions, including simplifying radicals.